Hello. So today let's discuss a new solution concept called rationalizability. Okay, so it is a solution concept, but sometimes we don't use that as a very often used solution concept. Okay, so because it's the most permissive possible solution concept. Okay, so in rationalizability, okay, so it's pretty long. So in this solution concept, so it still requires both players to be at least somewhat rational. Okay, and the players they know the other players, they're also somewhat rational. Okay, so it means that all the players they do not play dominated strategies. Okay, so that is basically the idea of this rationalizability. Okay, so basically it's the most permissive possible solution concept. Okay, so essentially it requires that both players they're somehow rational and no the other players they're somewhat rational. Okay, okay, so it means that the players do not play dominated strategies. Okay, so a strategy is called rationalizable if there exists some possible set of beliefs both players could have about each player's actions. Okay, that will still result in the strategy being played. Okay. So a strategy is rationalizable if there exists some possible set of beliefs. Okay, so beliefs is just a literal formally defined, and so it refers to some probability distribution over the other players' actions. Okay, so there's no state of the board here, so it's just some probability measure on the actions. Okay, so the beliefs, possible set of beliefs, both players could have about each other's actions. Okay, so that would still result in the strategy being played. Okay. All right. So the subset of the rationalizability is the dominant strategy equilibrium. Right. So, but a superset of that would be the Nash equilibrium. Okay. So, all right. So in the textbook of this chapter, so essentially they are introducing the rationalizability with the dominant strategies, the iterated elimination of dominant actions together. But we'll later, maybe in the next episode, we'll discuss the how to do that later, right? And link those concepts together. But in this one, we'll first formally define the rationalizability and see some basic properties of that. Okay, so basically we're examining the consequences of requiring that the player's choice be optimal given a belief consistent with the view that every player is rational, and every player thinks that every player is rational, and even further, every player thinks that every player thinks that every player is rational, and so on and so forth, right? And which is mentioned as in the first paragraph of the chapter on the textbook, right? So which would be really interesting to see. Okay, so now let's have a formal definition, and later we'll use some examples that we see previously. The battle of sexes and the prisoner's dilemma to show the intuitions of this. Okay. All right. So let's define that. So an action. Okay. Action AI is rationalizable. Okay. In the strategic game. Okay. And AI UI. Right. Now we are quite familiar with those things. So if for each J, okay, so there is a set, not a set, okay, ZJ, which is a subset of AJ, okay, such that, okay, so first, AI is an element of this ZI, okay, all right, so that's not hard. And second, so every action AJ in ZJ, okay, is a, okay, so notice that this is a for each player J, okay, so be careful. So every action AJ in ZJ is a best response to a belief mu J AJ of player J whose support is only a subset of Z minus J. Okay. So basically this is the definition, and it looks pretty, not easy to understand, right? So now let's use some examples that we demonstrated previously to try to have a better intuition on that. Okay. All right. So let's do the battle of sexes first. Okay. So if you recall that, so there's a man and a woman. So they're trying to go to see the Bach or Stravinsky. So if they go to the same place, then they have a higher utility. Otherwise, they will be having zeros, right? All right. So let's say this is 1 2 2 1 and 0 zeros, right? Okay. All right. So let's say for player 1, okay, so Bach is in the set of Z1, okay, for player 1, all right, so that's not her. And the belief for player 1 to play to have this action B, okay, so this belief is such that player 1 thinks that player 2 is playing Bach with 1 and playing Stravinsky with 0. Okay, so that's the distribution. That's the probability measure, right? 1 and 0. Then in this case, obviously, this B for player 1 would be a best response, right? As a best response to this 1-0 probability measure, right? So B is a best response to 1, 0. Okay. And then in this case, we can verify that this is a rationalizable action for player one, right? And correspondingly, so we know S is also in Z1. Okay. So as another example, so now we're trying to show that S is also rationalizable for player one. This is because for player one, for this S, if player two is playing 0 and 1, so player two is essentially playing S. Okay, so it means that S is also a best response, but it's to the measure with 0 and 1, right? So, and we can see that if sometimes the so basically those two actions, they're all rationalizable, right? And we know that those are both Nash equilibrium, right? Okay. All right. So that's a very good example of the rationalizability and rationalizable action, right? Okay. Now let's see some. So 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 as a reminder, so which is quite important is that we have those actions to be rationalizable. This is because that we could find some uh, beliefs right here, okay, such that those actions could be the best responses in those under those beliefs. Okay, so that's the first example, right? And let's use another example in the very beginning of our this series. Okay, so which is the prisoner's dilemma. Okay, so this is example 1 and example 2. All right, so in prisoner's dilemma, so each player could play defense or confess, right? D or C. D or C. Okay. All right. So let's say if both players they're defending, so they get 3 and 3. Okay, it's all right. But if one of those players they are choosing to confess, so who is betraying the other one, then in this case the one who is betraying actually gets a better outcome, right? So which has 4, but the one who is getting betrayed gets 0. Okay. If both are betraying each other, then we get 1 and 1, right? Okay. All right. So and we can see from this game, so there will be actually, so this D for each player would not be the rationalizable action. Okay, so to see why is that possible, let's just compare the expected payoff for each player. Let's say we're doing for player one first. Okay, so for this action D, all right, so the player one's belief with some action D. Okay, let's say player two is choosing the D or C with some probabilities. Let's say P and 1 minus P. Okay, so the payoff, okay, if player one is playing D, then the payoff would be actually this is the expected payoff, right? Should be 3 times P plus 0 times 1 minus P. So this would be 3P, right? But if player 1 is playing C, in this case, so the payoff would be 4 times p plus 1 times 1 times p, right? So in this case would be 3p plus 1, right? Okay, and obviously you can see that this 3p plus 1 is higher than 3p, right? Strictly higher. So it means that no matter what value this p takes, right? So it doesn't matter what is this p, okay? So that doesn't matter at all, right? So it means that in this case, no matter we have any p here, this payoff expected payoff for player one to play C would be higher, strictly higher than playing D. Okay, then in this case, player one will never play D, so D is strictly dominated. So in this case, then it doesn't satisfy the requirements that we need for the rationalizable actions, right? So player one's action D is not rationalizable, right? And it's strictly dominated. And we will affirmatively define the dominance later, okay? And link those concepts together. Okay, but for now we know that this doesn't satisfy the requirement. This the second requirement that we need for the rationalizability, right? Okay, and we can observe from this example is that both players they have the only rationalizable actions would be the C's, right? Okay. All right. So this would be a very brief introduction to the rationalizability and some examples, okay? And later we will show some other interesting results related to this. Okay.